All right, hey everybody. So this is kind of how our lessons are going to be from here on out. Um, I'm just going to go through the notes the same way as I would if we were in class. So stick with me. I know I won't have that interaction with you guys right away. So if I miss stuff, feel free to let me know. So let's get going into this. Okay, so we're in 1-4. We're talking about continuity and one-sided limits. Okay. So continuity at a point and on an open interval. The following functions are not continuous on open interval AB. Okay. Notice it's not continuous because we have this little hole in there. We have a nice little split right there where it jumps. And then we also have this little point that drops down below the hole. Okay? So, definition of continuity. A function is continuous at a point C if the following three conditions are met. Okay? And that means all three are met. Okay? Not just one, all three have to be met. Again, if you're making your cheat sheet, that's a big one to write down because you're going to be thinking about these every time you're looking at a limit. Okay? Notice these are all things 1, 2, and 3. These are things that we've looked at in our previous strategy, so we should all be familiar with them, but we need to make sure that we're checking all of these rules before we decide if the limit exists. Okay? So going on down, continuous on an open interval. Okay, a function is continuous on an open interval AB if it is continuous at every point C in AB. Okay? Continuous. Oops. At every point C in A, B. Okay. I'm going to try to write a little clearer for you guys too. All right. So every point has to be continuous, or every function has to be continuous over the open interval. Okay, so if a function is not continuous at a point C, then the discontinuities, could be either a removable disk, okay, which is like having a hole in your graph, all right, or we could have a non-removable disk. Which is like a vertical asymptote. That's what it is. Okay, vertical asymptote. Okay, with the removable disk, the function can be made continuous by defining C, and we'll see what I mean by that. And with the non-removable disk, it cannot be defined. Okay, it's non-removable, it's an asymptote, it's there. Okay, so let's hop on down to these examples, start ripping through these, and remember, guys, at any point you can pause this video and review it. Okay, that's the benefit of having these videos is you can look back at them at any time, get the information, ask questions about it, tell me what I've done wrong. Okay, so example 1. Okay, as we look at this, we know that we got just the x in the denominator. We know that our x cannot equal 0, right? So if our x can't equal 0, we know that this is not continuous, okay? It's not continuous at x equals 0. Okay, there's nothing we can do or cancel out to make this continuous, so it's going to be non-removable. Okay, and that's because we have that asymptote. Okay, now with number 2, okay, so from our previous, we learned that we can expand this out. Okay, that's the same thing as x plus 3 over x minus 3 over x minus 3. Right, we know that our graph, or if you do graph it, can know that it's something like this going through 6. Let's make that 3 because we have our hole right there. Okay? So we know that just looking at that graph, it's not continuous. X cannot equal 3 from that graph right there. Okay, so we know it's not continuous just from that, from the beginning. Because X cannot equal 3. Okay, but like as you saw, we manipulated this equation up here. All right, expanded it out so we could cancel out. And then when we plug in 3, and you have your f of 3, you can get 6. Oh, did it again. And you can plug in, when you see in your graph up here, you can, at 0.36, you have that hole. Okay. So this tells us that it's not continuous, it's removable. Because if we cancel stuff out, we can plug in our limit and we can find out what it is. Okay, so for this one specifically, we say the limit as x goes to 3 of f of x, all right, equals 6. But at the same time, gives you that empty set. Okay, so that's the difference. You see those first two problems give you good examples of what a non-removable and a removable is. Okay, a removable is something that if the function factors at the bottom term cancels. If when the function factors in the bottom term cancels, the discontinuity at the x value for which the denominator was 0 is removable, so the graph has a hole in it. Okay, so if you can cancel out the denominator and something in the numerator to make it so you can plug in your c and find the limit, that's removable. If you can't do that and you're just stuck with something that you have, like we have that x in the denominator, then it's non-removable. Okay? All right, let's just start going through these examples. Feel free to pause if you need to and look over them. I'm going to move a little fast. Okay? So just from looking at this piecewise function, we can see that they both meet at -1. We got an open and a closed interval. Okay? So we need to look at this from both sides. Okay, let's start looking at it from each of these graphs. If you start plugging in -1 for both of them. So for the first one, we'll plug in our -1, and you're going to get 1. If you plug it in for our bottom function, you get 3. Okay? So that's a good test. If you see that they come together at the same point, the same x point, but they get you different y's, that means that we're going to have a little split. Okay? So when you have a split, when you're coming at it from both sides and you see that the limit is different, then that means it is not continuous at x equals -1. Okay? All right, and we also know there's nothing we can do to this one because it's a split. It becomes non-removable. Okay? Hopping on over to 4, we can look again and see that they meet at the same x point, right? It connects together at x equals 3. Okay, but now let's plug in our f of 3 for both of our equations. F of 3, the first one, you get 5 over 5, which equals 1. All right, f of 3 of the second one, you get something like 9 minus 6 minus 2 equals 1. Okay? We get those same numbers. Look, we get 1 for both of them. That means it's going to be, you guessed it, continuous everywhere. Okay? Oh, man, I'm all over the place. You draw a little graph. I'll give you a little visual. Okay, if we got our 1, 2, 3 at 1. Okay, that's that point where they connect. Okay. You got this linear equation, something like that. And then you're going to get this. Something like a little loop at the end. Okay? See, no hole in the graph. It's continuous everywhere. Okay? Now going down to number 5. Number 5. Okay, again, come together at the same point. Let's plug them in now. Our f of 1 equals -1. F of 1 of the other guy equals 1. Okay? So, we have two graphs coming together at the same x point, giving you different y's. We got to split. Okay, so it's not continuous. Not continuous at x equals 1. And again, there's nothing we can do to this. It's a split or a vertical asymptote. Remember, it's non-removable. Non-removable. Okay? So those last examples, they're kind of leading us into this next little bit right here with one-sided limits. Okay? So one-sided limits, you use them to understand limits on a closed interval. So whenever you see this notation right here, this x to c plus c, they're asking you to look at the limit as it approaches that c from the positive side. So the limit from the right. Okay, with this guy over here, the c minus, okay, they're looking at it, they want you to check the limit from the left. Okay, some example graphs of this where this would come in handy is if you're looking at number 6, okay, you got the limit of the square root of x minus 3. Okay, if we sketch that graph out over here to the side, it should look something like this. All right, coming out that direction. All right, so if you take that limit from the positive side, right, your limit comes down at 0. Okay, if you looked at it from the right side, it's undefined, right? Our limit as x goes to 3 from the negative side, the square root of x minus 3 is not defined. Okay. So in number 7, we have a very similar graph, except if you guys notice, I should say, just go in the opposite direction. Okay, but now, hey, look, we're looking at it from the left side, okay, which means that from the left side, it approaches 0 again, right? As we look at the graph going from this direction, ends at 0. Okay, same as the other. If we looked at it from limit as x goes to just 2 from the positive side, all right, that does not exist. Or is not defined, I should say. Excuse me, not defined. Okay, there are no points to check. The point ends at 2. Okay, so we don't have anything to check. It's undefined. All right, hopping on down to x, or to x, excuse me, on to 8. We've got the limit of x goes to 3 from the positive side of the absolute value of x. Okay. Or actually, this is where we're taking those. You always round down. You know what I mean? These little L's. You're rounding down. When you have it like that, that means we're always taking the lowest number. So if you had 3.5 5, you're taking it down to 3. If you had 4.2, you're taking it down to 4. If you had 5.9, you're taking it to 5. Okay, you always drop it to the lowest integer. Okay, so if we look at this one, we sketch out a little graph. We're going to have those steps. All right, this kind of graph gives us those steps where you come up should look something like that. Okay, if you look at 3, all right, if we come on out to 3, 1, 2, 3, when we look at the approach from the positive side, we get a 3, right? We're just looking at it from the positive side. We're going to get a 3. All right, now if we come over to 9, real quick, because look, it's the same thing. It's just coming at it from the opposite direction. All right, if we come at it from 9, our limit's going to be 2. I'm sorry, if we come at it from the negative side. Why was I saying that? Okay, limit's going to be 2. Okay, if you look at this graph really quick, okay, coming from the negative side, right, we're going to get this 2. Okay, coming from the positive side, we're always going to get 3. Okay, that's what that graph is saying. That's how we're figuring out those limits. Okay, so if we look at both of these, okay, the limit of x goes to 3 does not exist. Okay, because look, it's a split, remember? If it's jumping around like that, it's a split. Okay, the two limits, if you approach from both sides, it has to be the same thing. Otherwise, the whole limit doesn't exist. Okay, and look, that leads us into the existence of a limit. Okay, what we just discovered there in 8 and 9. Okay, the limit of f of x equals L. Then the limit of f of x from the positive side and the limit of f of x from the negative side should also equal L. Okay, so by testing both sides, you should get the same limit. And if you don't, it does not exist. Okay, another little trick for our strategies. Okay, a couple more examples to finish out today. And we'll finish with a couple more definitions. All right, so on to number 10. Let's see, we're checking the graph x minus 2, but like we did before, we know that's one-sided. Okay, if you look at it from the positive side, you get a 0. If you do x to 2 to the negative side, it doesn't exist. There's no points over there. Okay, so the limit of x to 2 does not exist. I'm going to rewrite that the proper way. Okay, the limit of x to 2, x minus 2. Okay, so again, let's do the same thing over here for 11. Okay, we're going to look at it from the negative side, and we get a 0 from, or actually this is asking for negative 4 itself. So negative 4 to the positive gets you 0. Negative 4 to the negative gets you does not exist. Right? So if one of them doesn't exist, they all don't exist. Okay? If you get two different answers when you test it from both sides, it does not exist. Okay? So, just a good thing you want, maybe just put on your notes a little shorthand thing. Okay, is just something that I like to write things in these organized columns. Okay, you write the limit of x going to, oh my goodness, x going to c in the positive. You test the right side only. Okay. If you're taking the limit of x going to c minus to the c from the negative side, you're going to do the left only. Okay. And if you're taking the limit from x just straight up to c, you need to do left and right. They must agree, or it does not exist. Okay? So let's keep moving. Next page, we got more examples, always more examples. Okay, so we're looking again at these type of step graphs where we have the limit of x minus 3. Okay, they only want us to look at it from the right only. So if we look at x 0.1, this is kind of where those tables would come in handy. So like I make a little table. If we got our x equals 5.1, 5.9, 5.99. Okay. So that means our limit would be 2.1. Right, we take that, which equals 2. All right, this would give us a 2.9, which gives us 2. This one gives us a 2.99, still gives us 2. Okay, so as we approach 5 from the positive side, so we're using all those positive values, okay, we kept it under 6, it always takes us to 2. Okay, so that means that our from the right side limit, 2. Okay? 13. We're only looking at it from the left only. Look, we got this nice little negative sign. Left only. Okay, so we can just look at some of our x's. If we plug in things a little less than 4, so our x equals 3.9, right? Then we're going to take the step of 8.9, which is going to give you 8. Okay, since we're only testing the left side, all we have to do is find the limit from the left. It's 8. Okay, 14. It's asking us to test it from, no positive, negative, both sides. Okay, so first let's test it from the positive side for our positive 2. Okay, let's just throw in a 2.1. Okay, that'll give us a little step of negative 1.9. Takes us to negative 2. Okay, now let's look at 2 from the negative side. So we're going to plug in a 1.9, which is going to take us to the step of 2.1, which equals negative 3. Ooh, so we got 2 different limits going from the right and the left. What's that mean? It means it does not exist. Okay, testing both of them. 15. Okay, look again. Nothing. So we're testing both. Okay, so if we look at 3 from the positive side, 3 from the negative side, we should get 1, and we get 1. Okay, I plugged in 3.1 in my head. I plugged in 2.9 over here. Okay, they both got me 1. My limits are the same. So it tells us the limit of x going to 3 equals 1. But this is one of those interesting ones because we know that this does not exist. All right, so this is one of those weird ones where it gives you a limit, but we have to know that the limit of x going to 0 does not exist. Okay, so that was, so 16. I'm going to give you a second to do 16, A and B on your own, and tell me what you come up with. So pause the video, do it, and when you're done, unpause it, and we'll go through it. All right, excuse me. So 16, here we go. Again, we only need to do the right side only for 16A, and we're doing the left side only for 16B. So we're starting with 16A, or this, we'll call this one 16A, okay? So we're going to plug in a couple x's that are on the positive side. When we do this, when I use an x equals 3.1, and then let's just say an x equals 3.0001, something crazy like that. Okay, when we plug those in, we get 0.968, and we're going to get 0.9999. Okay, again, these both go to 1. Okay, they're getting infinitely close to 1 as we get infinitely close to 3. All right, so now let's look at the left side over here. Okay, we got, let's use x equals net 2.9 and x equals 2.9999. Get crazy. Okay, for this one, sorry about that. For this one, I got 0.6899, and for this one, I got 0.66669. Okay. This might be harder to see because it's not a whole integer, but these are getting infinitely close to 2/3. All right, notice we have two different limits from going from the right side and going from the left side. So what's that tell us? The limit of x over x as x goes to 3 does not exist. Okay? So let's finish up with a couple definitions and a little example here to explain the definition. So, definition of continuity on a closed interval a, b. Okay? A function f is continuous on a closed interval a, b if it is continuous on the open interval a, b, and if the limit of x coming from the positive side of a of f of x equals f of a, and the limit of f of x coming from the negative side equals f of b. Okay, notice this x is going towards the negative side of b, this is going from the positive side of a, so it's hitting both ends of this closed interval. Okay, so the function is continuous from the right and continuous from the left. Okay, so some examples. It's always easier to jump into these examples. So f of x equals the square root of x. All right, we know that's graph looking something like that. All right, we know it's continuous from 0 to infinity. All right, for all x greater than 0. Okay, You see how it's only continuous in that contained interval. All right, 18, we got to do a little bit more work to get this graph. This one might not just pop out to you right away. So I like to set this up as we got 4 minus x is less than or equal to 0. Okay, if we start moving stuff around, I'm sorry, this is x squared. Okay, if we start moving that 4 over, you're left with the x squared less than or equal to negative 4. Okay, which gives us that, get rid of that negative sign, flip your sign. Like that guy. Okay, and this should give us x is less than or equal to 2. X is greater than or equal to negative 2. Give us that little interval. Or you can write it like this. Okay, so our points are on this closed interval. So if we only plug in points from these spots, we get 0, negative 2. Okay, we get a positive 2, 0. I'm sorry, negative 2, 0, 2, 0. If you plug in 0, you're just going to get a nice 2. So this graph gives you that half circle. Can't even draw a half circle. But, all right, thanks for sticking with me today, guys. That's it for our 1-4 day 1 notes. Stick around for more to come.